we have already learned about the structure of the PN junction, its formation and its internal mechanism of operation. A semiconductor diode is basically a PN junction with metallic contacts provided at the ends for the application of an external voltage. Symbolically, it is represented as shown in the figure. Now, the direction of the arrow indicates the conventional direction of current when the diode is under forward bias. In the PN junction, the interaction between the excess carriers from the P and N side create a depletion region. We have the diffusion of holes and the drift of electrons from the P side and vice versa, until the depletion region is fully formed. Once this happens, there is no further migration of charge from either side. Now, what is this forward bias? A diode is said to be in forward bias when an external voltage is applied across it in such a way that the P side is connected to the positive terminal and the N side is connected to the negative terminal. The applied voltage drops across the depletion region. The applied voltage in this case is V. The direction of the applied voltage is opposite to the built-in voltage represented by V0. Thus, the effective voltage across this barrier is V0 minus V. In turn, the width of the depletion region will decrease because of the application of the external forward voltage. When the external voltage V is much less than V0, only a small number of carriers will have enough energy to cross the depletion region, and so there will be a very small current. But as V is increased, the depletion region will decrease and the barrier voltage will also decrease. As a result, more and more carriers will be able to cross the junction. Thus, with the increase in applied forward potential, there is an increase in the flow of current. Another factor we have to remember is minority carrier injection. When a PN junction is forward biased, electrons from the N side cross the depletion region and reach the P side, where they are minority carriers. Conversely, holes from the P side will cross into the junction and reach the N side, where they become minority carriers. Thus, at the junction boundary on each side, the respective minority carrier concentration increases significantly compared to locations far away from the junction. This process under forward bias is known as minority carrier injection. Now let's look at reverse bias. A diode is said to be in reverse bias when an external voltage is applied across it in such a way that the P side is connected to the negative terminal while the N side is connected to the positive terminal. So this is the opposite connection compared to forward bias. The direction of the applied voltage is same as the built-in barrier voltage. So the effective voltage across the depletion region is increasing. It is V plus V0. And thus the width of the depletion region will also increase. The flow of carriers is suppressed and the diffusion current decreases enormously. The electrical field is such that an electron on the P side and a hole on the N side come close to the junction and are swept across. Thus, the drift current in this case is on the order of milliampere, which is much greater than the case in forward bias. Thus, the current in case of reverse bias of a diode is not dependent on the external voltage applied. However, when the external voltage applied exceeds a threshold known as the breakdown voltage, the current will increase sharply. This is known as the breakdown region, as we can see here in the VI characteristics of a silicon diode. Now, here we see that when the diode is in forward bias, that is, the voltage is positive, P side is connected to positive and N side is connected to negative, there is almost no current until a specific voltage is reached. In the case of silicon, this is approximately 0.7 volts. This is the exact value of the barrier voltage across the depletion region for a silicon diode. The moment the external voltage reaches this value, the depletion region is completely collapsed, and thus we have a major increase of charge carriers across this junction. On the other hand, if we were to reverse bias the diode, that is, we are connecting the positive terminal of the battery to the N side and the negative terminal to the P side, we are in fact increasing the depletion layer width, we are increasing the barrier voltage, thus we have a very small current flowing in the reverse direction. But remember that this current, known as reverse saturation current, will remain constant only up to a certain value of reverse voltage. As the applied reverse bias voltage exceeds the breakdown voltage VBR, there will be a sudden increase of flow in the reverse direction. The threshold voltage for silicon diodes is in the range of 0.6 to 0.7 volts, whereas for germanium diodes is in the region of 0.2 to 0.3 volts. Now let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.